Good morning, everyone. My name is Jessica Christian, and I have been studying tomography of quantum and classical optical states in Dr. Ramon Hafezi's lab. So I've been interested in quantum physics for a very long time because I think it's very much the future. Optics, specifically, the study of electromagnetic waves and light, is already so prevalent in our society, but with the advent of quantum computing and quantum information technology, there's so much more potential there. The states that we specifically studied in our experiment, the HV state and the noon state, are particularly interesting because the HV state is suited to use as a qubit in a quantum computer, which refers to it's the analog for a classical bit, but a qubit contains far more potential because rather than being in an on or off state, it can be in any position between 0 and 1, any on-off composite. While a noon state is responsible for advances in measurement accuracy or metrology, because firing noon state entangled photons at any small object rather than firing classical single photons can produce measurement accuracy which very quickly approaches the Heisenberg limit. My process, tomography, is essentially a method of evaluating any quantum state. We do this by observing the quantum state in a series of bases, and by taking that composite picture all together, composing a density matrix, which you see to your right. So the bases that we study are polarization oriented. So polarization simply refers to the direction that an electromagnetic wave takes in space. And if you look at the matrix on the right, you can see at the top it says rho is the sum of a density weight, so that's p sub I, times any eigenstate of the basis that we're talking about. So in the polarization bases, that would be horizontal and vertical, so horizontal and vertical, or circularly polarized, or diagonal and anti-diagonal. So you can see it's very visual and a very tactile situation. I've put a sample density matrix here, and if you look along the diagonal, you can see that the first and last values are the highest. So it's called a noon state because the values along the diagonal are proportional to n, 0, 0, and n, which tells us that the first and last states, horizontal, and vertical, vertical, are the only possible states within this particular quantum state. So our method was to pump photons from a 780 nanometer pump into a down converter. And the down converter is there to divide the photons into two beams, one of which is polarized in a certain direction, and the other of which is polarized in another. And the direction that the photons were polarized varies based on our setup. On the far right, you can see the half-wave plates, quarter-wave plates, linear polarizers, and of course the detectors. And these are used to measure the bases that we're evaluating n. So our first state, the HV state, which is most useful for qubit use, is we were able to get a fairly accurate representation of the state. And if you look to the matrix on the left-hand side, you can see that the four central columns are very close to 0.5, which is our ideal value. This is in contrast to our noon state, which is more useful for metrology. So our four outer peaks are, again, very high, but we got a lot of background information, so the fidelity was fairly low. In addition, this is our graph of absolute values, but our real values are there, and you can see that there's a difference between the heights of the absolute values and the heights of the real values, which tells us that some of our data is in the imaginary plane rather than the real plane. And this small amount of error came from inherent issues with our SPDC crystals and our optical fibers. While it was passing through, a dispersion was created, which changed the phase of one of the light beams. And through the optical fibers, there was also an additional dispersion that compounded between those two. So in the future, ideally, we'll be able to adjust the phase using a phase compensator like a quarter wave plate. And after being able to do so, once we increase detector availability, we'll be able to produce 3 and 4 photon noon states and be able to observe these properties as they're extended to more and more particles and bodies. And finally, I'd like to acknowledge the University of Maryland and the NSF for sponsoring this research.